There is a building in Istanbul that has survived at least 10 documented major earthquakes, and an unknown number of smaller ones. Over 15 centuries of continuous seismic activity in one of the most geologically active corridors on Earth. Not survived intact. Not survived without damage. Survived in the sense that it is still standing, still structurally sound, still carrying the load of an enormous dome above an open interior floor, after every major tremor the Bosphorus has sent through it since the year 537. The Hagia Sophia was built in 537 AD. The region it sits in, the Bosphorus Strait between the Black Sea and the Marmara, has been shaken by documented major earthquakes in 553, 557, 558, 869, 989, 1344, 1509, 1719, 1766, and 1894. Most of those earthquakes damaged the building. The dome partially collapsed in 558. Parts of the exterior buttressing failed in 989. The minarets added by the Ottomans were damaged and repaired multiple times. And yet, the core fabric, the walls, the main piers, the central dome structure rebuilt in 562, has not failed again in 14 centuries of continuous seismic loading. The reason has been sitting in the walls the entire time, and structural engineers did not understand it fully until the 1990s. It is the mortar, not the design, not the geometry, not the thickness of the walls or the skill of the builders, or the particular quality of the stone. The mortar, the substance that fills every joint between every brick and stone in the Hagia Sophia, a grey, unremarkable paste that the Byzantine builders mixed from lime, crushed brick dust, and a volcanic ash called pozzolana, is still curing. After 1,500 years, the chemical reaction inside those walls has not stopped. The mortar is still getting harder. And the mechanism by which it does this is the same mechanism that allows it to seal small cracks before they become large ones. The Hagia Sophia's walls, in a precise and measurable physical sense, are still healing themselves. There is a detail that makes this harder to accept, not easier. This was not intentional. The Byzantine builders did not design self-healing mortar. They used pozzolanic lime mortar because Roman engineers before them had used it, because it had proven durable across centuries of Roman construction, and because the volcanic ash that gave it these properties was available and cheap in the ancient Mediterranean world. They knew it worked. They did not know why it worked. The mechanism, the ongoing chemical reaction between calcium hydroxide and volcanic silica and alumina that produces new crystalline structures indefinitely, was not described in any text they would have read or written. It was not discovered until modern materials, science had the tools to look inside hardened mortar at the molecular level. They built with it, by inheritance, by tradition, by the accumulated practical knowledge of Roman construction passed forward across centuries, without understanding the chemistry they were encoding into every wall they built. And that inherited ignorance, that fidelity to a practice whose mechanism they could not explain, is part of why the Hagia Sophia is still standing. We get to the full story. But first, what mortar actually is, and why the difference between ancient and modern matters more than most people realize. Constantinople, 532 AD. The city is still burning. It has been burning for 5 days. The Nika riots, the most violent urban uprising in the history of the Byzantine Empire, have left entire districts in ash. The Church of the Holy Wisdom, the Hagia Sophia, has been reduced to rubble. 30,000 people are dead. And the Emperor Justinian, having put down the riots with force, has decided to build something that has never existed. He wants it finished in 5 years. The men who will mix the mortar for the Hagia Sophia are not architects or mathematicians. They are laborers. They work in teams organized around the mortar pits, large wooden troughs set up near the building site where the raw materials are combined by hand. The lime comes from burning limestone in kilns. The crushed brick dust, called coxiopesto in later Italian usage, comes from broken and rejected brick fired in the same kilns. The pozzolana, the volcanic ash that makes this mortar different from every modern equivalent, comes from deposits in the Aegean region, particularly from the island of Santorini and from the volcanic fields around Naples, traded and shipped across the Mediterranean since Roman times. The mixture is combined with water in the pit. The laborers work it with wooden paddles, folding and pressing until the consistency is uniform. It smells of wet mineral, of something slightly acrid from the lime, of earth. In the summer heat of Constantinople, the pits have to be covered when not in use to prevent the surface from skinning over before the mortar is used. A freshly mixed batch has a working life of a few hours in warm weather. After that, it begins to stiffen and must be discarded. This means the mortar pits are in continuous operation throughout the construction season, mixing in small batches, consuming enormous quantities of raw material. The Hagia Sophia, at peak construction, used an estimated 100,000 workers. The mortar supply chain, kilns, quarries, shipping, mixing, was an industrial operation by the standards of the ancient world. But here is what none of those laborers knew about what they were making. When lime and volcanic pozzolana are mixed with water, a chemical reaction begins. Calcium hydroxide from the lime reacts with the silica and alumina compounds in the volcanic ash to produce calcium, silicate hydrate, and calcium, aluminate hydrate. Crystalline minerals that grow slowly within the hardening mortar, filling the microscopic pores in the matrix and bonding to the brick and stone on either side of every joint. This reaction does not stop when the mortar hardens. It continues. Slowly, almost imperceptibly, new crystals continue to form in the mortar matrix, over decades, over centuries. The mortar that was mixed in Constantinople in 532 AD is a measurably different material today than it was when it was laid. It is harder, it is denser. Its internal crystal structure is more developed. Modern materials scientists who have extracted core samples from the Hagia Sophia walls and analyzed them under electron microscopy have found mortar that is still in the process of mineralogical transformation, still growing new internal structures, still getting stronger. 1,500 years, still curing. But the curing is only half of it. The more surprising property is what happens when the mortar is stressed. When an earthquake shakes a masonry building, the walls flex. Fractionally, microscopically, but they flex. A completely rigid structure under seismic loading does not flex. It cracks, and the cracks propagate. A structure with a degree of flexibility absorbs the movement and returns to position. Modern engineers solve this with steel reinforcement, which provides controlled flexibility and prevents crack propagation. The Byzantine builders had no steel in their walls. What they had was lime mortar with a specific property that modern seismic engineers have only recently begun to study systematically. When a crack forms in pozzolanic lime mortar, as it will under seismic loading, under settlement, under the slow movement of a heavy masonry structure over centuries, water infiltrating the crack dissolves calcium hydroxide from the surrounding mortar matrix. That dissolved calcium hydroxide migrates through the crack, and when it contacts carbon dioxide from the air or reacts with additional silica compounds, precipitates as calcium carbonate or new calcium silicate crystals directly inside the crack. The crack fills itself. Not completely, not always, not quickly, but measurably. Samples taken from cracks in the Hagia Sophia walls show this process in evidence. Crack surfaces lined with secondary mineral deposits that formed after the crack opened, reducing the crack width, rebonding the surfaces, partially restoring the structural continuity that the crack had interrupted. The walls are not static. Under the right conditions, they heal. Now think about what this meant across 17 earthquakes over 15 centuries. Each earthquake introduced micro-cracks throughout the wall fabric, hairline fractures in the mortar joints, slight separations at the interfaces between brick and mortar. In a modern building with Portland cement mortar, these cracks are permanent. They accumulate. Each earthquake adds to the damage of the previous one. Over enough cycles, the accumulated damage reaches a threshold and the structure fails. In the Hagia Sophia, each earthquake introduced cracks that then, over the subsequent years and decades, partially healed. The structure arrived at the next earthquake not in the damaged state left by the previous one, but in a partially recovered state. The damage accumulated more slowly. The threshold was never reached. This is not speculation. The 1990s finite element analysis of the Hagia Sophia, the most comprehensive structural study ever conducted on the building, found that the seismic performance of the structure could not be adequately explained by its geometry and mass distribution alone. The models kept underestimating its resistance. When the researchers incorporated the ongoing curing and crack-healing properties of the pozzolanic mortar into their models, the numbers aligned. The mortar was providing a measurable contribution to the building's seismic survival that had been invisible to every previous analysis. Here is what makes this genuinely difficult to absorb. The builders of the Hagia Sophia did not optimize for seismic performance. They optimized for speed, 5 years, Justinian's deadline, and for the visual effect Justinian wanted, and for durability in the general sense that any competent builder of the period would have understood. The seismic properties of pozzolanic mortar were not on their agenda because they did not know those properties existed. But they used a material that had been proven across 5 centuries of Roman construction in regions that were also seismically active: Rome, Pompeii, the entire Italian peninsula. Without anyone explaining why it worked so well in those conditions, the track record existed. The mechanism was invisible. And the builders followed the track record. This is the pattern that appears across every great building in this series. At Durham, where the carved spiral patterns were quality control before they were decoration. At Florence, where Brunelleschi used a brick arrangement he could not mathematically prove. At Beauvais, where the 14th century rebuilders calibrated their correction to the specific failure, without the structural theory to explain why their calibration was right. In every case, a solution that worked before anyone understood why it worked, transmitted forward through practice and material knowledge, producing results that modern analysis confirms were precisely correct. The builders of the Hagia Sophia were the oldest example in this series of that pattern, and the mortar is the oldest evidence of it. Now, the quarrying. Because the pozzolana had to come from somewhere, and where it came from tells you something about the scale of the operation. The volcanic ash deposits closest to Constantinople, and most reliably available in the quantities required for a construction project of this size, came from the Aegean volcanic field, from deposits associated with the Santorini eruption complex, and from volcanic outcrops in Asia Minor. Getting this material to Constantinople in 532 AD meant ship transport across the Aegean, in vessels that would have been carrying dozens of other cargoes simultaneously, competing for space with the grain shipments that fed the city, the marble that was arriving from quarries in Greece and Turkey and Egypt. The logistics of the pozzolana supply were embedded in the larger logistics of running a city of perhaps 500,000 people. The mortar laborers at the building site received their volcanic ash as one item in a continuous flow of materials arriving by sea. They did not know where it came from in the sense of having visited the source. They knew it as a grey powder that arrived in sacks and was added to the lime in specific proportions that produced the consistency they had been trained to recognize. Those proportions, the ratio of lime to pozzolana to crushed brick to water, were transmitted orally and practically from senior mortar workers to apprentices, verified not by measurement, but by feel. The correct mortar, worked with a paddle, had a specific resistance and a specific color and a specific smell. An experienced laborer could tell by mixing a batch whether the pozzolana was the right grade, whether the lime had been properly burned, whether the water ratio was correct. None of this was written down in any surviving document. It was embodied knowledge, carried in hands and noses, and the accumulated experience of men who spent their working lives at mortar pits. That knowledge was lost, not at once, not deliberately, but through the accumulated disruption of the centuries that followed the Byzantine period. When the Ottomans began major construction in Constantinople after 1453, they mixed their mortar differently. When European builders of the medieval and Renaissance periods built their great structures, they used locally available materials in locally developed proportions that did not always include volcanic pozzolana, because volcanic ash was not always available, and the understanding of why it mattered had not travelled with the practice. Portland cement, the mortar material used in virtually all modern construction, was patented in 1824. It is faster setting, stronger in compression, and more consistent than any lime mortar. It is also brittle, does not continue to cure after setting, and does not self-heal. A crack in Portland cement mortar is permanent. Modern structural engineers manage this with steel reinforcement, which gives the structure a different kind of resilience. Controlled cracking along predictable lines, rather than crack healing. The two systems are not comparable in simple terms. Portland cement with steel reinforcement produces structures that are stronger in most measurable ways than ancient pozzolanic masonry. But, in one specific property, the ability to sustain repeated seismic loading over very long time periods without accumulating structural damage to failure, the ancient material does something the modern one does not. Researchers at MIT, Harvard, and laboratories in Italy and Switzerland studying Roman concrete published findings in 2023 confirming that the seawater environment in Roman maritime structures was actually strengthening the concrete over time, with mineral crystallization in the crack interfaces measurably exceeding the original matrix density in some locations. The ancient Romans were building structures that got stronger when they got wet and cracked. They did not know this. Their engineers recorded that the material was durable. They did not record the mechanism. The same mechanism in the terrestrial version is what keeps the Hagia Sophia standing. Walk into the Hagia Sophia today. The main nave is a vast hall, the scale initially confusing because there is no nave in the conventional sense. No long axis with a distant apse, just an enormous central space under a dome that floats above a ring of 40 windows. The dome is approximately 31 meters across and 56 meters above the floor. The light comes from below the dome in all directions simultaneously, from those 40 windows and from the subsidiary half-domes and their own windows, creating a luminosity that has no single source and no shadow. The walls are mostly bare now or covered in Ottoman calligraphy panels and the traces of removed mosaic. But run your hand along a wall surface where the plaster is missing and you touch the original Byzantine brick. Small, thin, reddish-brown bricks set in mortar joints that are sometimes as thick as the bricks themselves. The mortar is grey and hard, harder than the brick it bonds. You cannot scratch it with a fingernail. That mortar was mixed by hand in a pit in the summer of 532 AD by men whose names no document records, in batches that had to be used within hours, following proportions transmitted to them by the men who trained them, which had been transmitted by the men who trained those men, in an unbroken chain of practical knowledge reaching back through the Roman construction tradition to builders who had first discovered, by accident or experiment, that the grey volcanic powder from the Aegean made lime last longer than lime alone. The chain broke eventually. The knowledge dispersed. The mechanism was forgotten, but the mortar is still in the walls, still curing, still, when a crack opens, slowly filling it with new mineral growth. Still doing what it was made to do, 15 centuries after the hands that made it were dust. 10 documented major earthquakes. 14 centuries since the dome was last rebuilt. The walls are still there, still holding, still getting imperceptibly stronger in the dark. They built with what they knew worked, without knowing why it worked. And what they built has outlasted every explanation they could have given for it.